We're going to continue talking about time and frequency analysis for signal processing, and I'm going to introduce the concept of what's called the Bode plot. The Bode plot is a way of understanding both the amplitude and phase response of a signal in an LTI system and starting to rethink how signals look like in this processing just by this very standard way of approaching it, which is this Bode plot idea, which both looks at amplitude and phase of the response of a system. And by understanding the amplitude phase response of a system, you can actually completely characterize what it's actually doing overall in a signal processing framework. So this is a really important way to visualize LTI systems in practice, especially complex ones. That's a very standard thing, is to look at the Bode plot to understand what's going on in those systems. So Bode plots. We're going to start off with a demonstration system, which is going to be a differential equations system, and we're going to develop the Bode plot out of this system to start understanding how to characterize this. So the system we're going to start with is a first order differential equation here, some time constant tau in front of the first derivative plus y driven by x. Okay, so x is our input signal, y is our output, and we want to start to understand the response of the system, and we're going to move it towards understanding it in context of a Bode plot. So this system, we can basically characterize it by taking the Fourier transform. So the Fourier transform of this first term, right, of the derivative is I omega times y. That's what you get here. And the Fourier transform of y is y, and then of x is x. So there you are. You have something like this that you can do one more level of manipulation, which is you collect your y terms and divide by x. Just manipulate this equation here into this form here, and y over x is equal to h. So that is the Fourier transform of the impulse response, which is now given by 1 over 1 plus I tau omega, which I just simply got from manipulating this equation here. So again, we've done this type of problem previously, but now we're going to dig down a little bit on this response function and both look at its amplitude and its phase response, because that's going to allow us to have a richer view of what's going on, but it's also going to allow us to construct the Bode plot. So first of all, let's look at this signal in the Fourier domain, or it's the response in the Fourier domain. There it is. And if we wanted to understand what it looks like back in the time domain, all we have to do is look this up in a Fourier transform table and invert it. And what we're going to find from the inverse Fourier transform is h of t is 1 over tau, that's the time constant, e to the minus t over tau, u of t. Ut is essentially the step function. So it comes on at time 0 and it decays down. So this is a pretty simple pairing to understand. That's its frequency response, that's its time response. So this is the impulse response in time due to a delta function kick that you discover not from the delta function, but by looking at the input-output pairs of those differential equations that you have. The step response itself then is to say, if I want to understand the step response, I take the step response is h, which is the time response, convolved with u of t. So my input is just the step, 0, and then it's on at 1. And this is very simple to work out because, in fact, now I'm just going to convolve, I've got these two convolved with each other. I can take the Fourier transform of this times the Fourier transform of that, invert, and here is, in fact, the result of that inversion. What you find, it's a very simple thing to actually calculate the time response. It's 1 minus this exponential times u of t. So we now know the time response of this. And so here it is in plot. So what you have here, the signal comes, this is what h of t is. It's 0, comes on, goes back down. So that's the fundamental response due to a delta function kick. And we discovered this response by taking the Fourier transform of the actual input-output relationships, were differential equations. And the step function, if I hit this problem with the step function, here is its behavior. It rises to the value of 1, and it takes a certain amount of time to do that. There's like a half-life, you can think about it, to come up to this value here. Okay? So this is the response. Here is, this is the response to h of t, and this is a response to a step function input, and that's s of t, or So it's y given that the input is a on step u of t. Okay, so now what we're going to do is we're going to look at this a little bit more carefully. This is a very simple problem, but now we're going to start looking at this from the point of view of what's called a Bode plot. And so what the Bode plot is you're going to take your response to this function, which we already derived, which is 1 over 1 plus I tau omega. Here it is in the frequency domain. And the way that the Bode plot is defined is one of the things we're going to look at is this quantity right here. 20 times log 10 of the absolute value of h. Okay? And so the units of this are going to be decibels. So this historically, there's a reason why we want to put it in this log format in terms of decibels. But overall, what's going to do is going to put things on log scales, and we're going to start looking at the intensity response of the signal on the log scale, because what it helps emphasize a little bit is big responses and small responses. It shrinks all those up a little bit to make them a little closer in the same size because of the log itself. So the absolute value of this, by the way, of this function, is pretty easy to calculate. You just take this times its complex conjugate square root, which is given by here. And if you look at this, this is just 1 plus omega tau squared raised to the negative 1/2 power. So this negative 1/2 power, when we look at the log here, right, 20 log 10 of this, which is given by here, this negative 1/2 can come out front to give us negative 10 log 10, 1 plus omega tau squared. So what we're going to plot in a Bode plot is this quantity here on the y-axis, and on the x-axis, it will be also a log scale of the frequency. So if we plot that, that's going to be part 1 of our Bode plot. So this is what we're looking at. But before we plot that, some very simple things to look at. We can ask questions like, what happens if I have very small frequencies? So in other words, omega is very small, near 0, then look at this here. So this is going to be something where, well, if omega is near 0, then log 10 of 1 is 0. So we have something very simple to compute. So near very small frequencies, this thing here is around 0 dBs. But then when we go to very high frequencies, you can actually show that, in fact, it goes to something like this. This quantity here goes to just something like omega dominates. And so you can actually just see that it's going to be a in log scale, it's going to be like a linear slope with as a function of omega in the log scale. So these are two of asymptotic approximations for small frequencies and high frequencies. And you'll see this borne out here in our part 1 of our Bode plot. Part 1 of our Bode plot is this 20 log 10 of the absolute value of h. And this is as a function of omega on a log scale. So 0.1 tau, 1 tau, 10 tau, 100 tau. And so again, we approximated this near 0 over here, and we approximated this to be a linear slope over here. And so that's what you're seeing over here is this linear slope here. So this is the overall Bode plot, the intensity response h on the log scale. And you have this interesting feature here where it's pretty flat. It takes a turn down. So it's like linear here, slope 0, slope omega. And you get this fold over point here. And so we have approximations for both of these. And so this is kind of what a Bode plot looks like. It tells you the response h in this log coordinate system, right, as a function of log also of frequency over here. And this Bode plot is super important because it's starting to characterize what the signal looks like overall. At least this is the intensity of the response h. The one last piece of the Bode plot is then to look at the phase response of the signal as well. So you get both the phase and the intensity. This whole chapter is about the time frequency, so really about the amplitude and phase of what's going on in the Fourier domain is going to really matter for us in terms of manipulating signals. The last couple lectures I've show you that if you also manipulate the phase of the signal, it not only can warp the signal, but it can move it in time. That, along with this filtering, which is exactly what you're seeing here, determines what's going to come out of your system. So let's actually look at the phase, because that's the second component of this. So here is your signal, H, again, and you can actually compute the arctan of the real over imaginary part of this thing, or imaginary real part, and you find this thing to be the inverse tangent, minus inverse tangent. So this is just looking at the phase of this imaginary number. It's not that hard to compute this, and that is the inverse tangent of omega t. So that gives us now the phase of this signal H. And remember, part of what we're doing here is not only looking at the intensity, but looking at the phase. So now we have the phase. We already got the intensity. So now we can plot the phase. And the phase goes from 0 to the value of negative pi over 2. And that's just determined by this inverse tangent. So there we go. That is the phase response of this very simple filter or signal of this response function for this differential equations we started with. And overall, the Bode plot is composed of these two pieces. So again, on the x-axis is the frequency as a function on a log scale. So, right, we're looking at the frequency components on a log scale, and that's kind of important. So what it does is it sort of stretches things out in just the right way, the log base 10 scale, for us to look at it in a more interesting light. This is on a dB scale because we've taken that intensity of H, put it on a log scale, divide it and multiply by 20, and then you can see this response in its intensity, and this is the phase response of a signal. So part of what a Bode plot does is if you're processing a signal through a system, if you can produce a Bode plot, it's telling you what's going on in terms of like a filter plus the phase content. And these two pieces are the critical pieces you need to manipulate a signal to a desired output. So the Bode plot becomes like essentially a core characterization of that signal processing and signal processing design. So keep that in mind. You'll see lots of Bode plots in signal processing overall because they're just a very intuitive way to start thinking about how the shaping of signals is happening as a function of frequency, both in terms of the intensity and phase in the Fourier domain.